Dr. JUMADI. My name is Vinod Shivadarshan. My metric number is DN2034. I'm representing my electronic communication system project group to explain about the circuit diagram that constructed by me, and the following result will be explained further by my fellow groupmate Vivekan. So without any further ado, let's move into the explanation. So the circuit constructed over here is an active bandpass filter designed using four operational amplifiers, resistors, and capacitors. The circuit uses the 741 operational amplifier, a commonly used general purpose operational amplifiers. So this filter design incorporates both high pass and low pass sections to achieve a bandpass response, allowing frequencies within a specific range to pass through while attenuating frequency outside this range. So I will explain each one of the section more in detail, starting with section 1. So this stage is configured with the capacitor C1 with 680 nanofarad in the feedback loop, and capacitor C3 and C2. So C2 is 3 nanofarad and C3 is 2 nanofarad. In both of these capacitor in conjunction with resistors like R1, R2, and R3. So to form these conjunction are made because to form a high pass filter. So this first section, the configuration allows high frequency to pass while attenuating low frequencies. So jumping into the second operational amplifier, this stage includes resistor R4, R5, both are 560 kilo ohm, and capacitor C4 with 5 nanofarad and C5 with 470 picofarad in the feedback loop. This configuration works together with the first stage to further refine the bandpass characteristics, typically focusing on mid-range frequency. So moving on in the third section over here. So this stage features resistors R6 1 kilo ohm and R7 1.2 kilo ohm, and capacitor like C6 with 3 nanofarad, C7 2 nanofarad, and C8 680 picofarad. This stage is designed to function a low pass filter, allowing low frequency to pass while attenuating high frequency. So finally, the last section of the circuit, this stage consists of resistors like R8, R9 560 kilo ohm, and capacitor like C9 and C10. C9 is 5 nanofarad and C10 is 470 picofarad, along with R10, the resistor R10, 5.6 kilo ohm. So this stage further process the signal to finalize the bandpass filtering effect, ensuring that only the desired frequency band is allowed through. Sorry. So the circuit function. So starting with the high pass filtering. The first stage with the operational amplifier acts primarily as a high pass filter, allowing frequency above a certain cutoff to pass through. So here occurs the mid-frequency processing on the second stage, refines the signal, often targeting the mid-range frequency to enhance the bandpass effect. So next will be the low pass filtering on the third stage, act as a low pass filter, ensuring that frequencies above a certain cutoff are attenuated, and final stage, that is the final section. Here, the fourth stage with fine tunes the overall band pass response, ensuring that the circuit allows a specific band of frequency to pass while attenuating those outside this band. So the circuit demonstrated over here is a multi-stage bandpass filter using 4 operational amplifiers and a combination of resistors and capacitors. Each stage is designed to contribute to the overall frequency response. The first stage as a high-pass filter, sorry, the first stage as a high-pass filter, the second and fourth stage for mid-frequency processing, and the third stage as a low-pass filter. The design effectively combines this filtering stage to create a Butterworth bandpass filter, which is known for its smooth frequency response within the band pass band. The circuit's output obtained through multi-sim simulation. This whole circuit is constructed in multi-sim software, shows the magnitude and phase character of the filtered signal, verifying the functionality of the both low pass and high pass filtering. So as we can see here, when we run, the particular circuit will be run successfully, and we can see the graph over here. So this section will be further explained by my fellow groupmate Yuvegera. That's all from me, Doctor. Thank you.
Hello, Doctor. My name is Yuvegan Rao. So I am going to represent my team, my group, for to explain on the results we have gotten from the multi-sim. As you can see, I am presenting our graph. As you can see, the one on the top is our gain plot, and then the one on the bottom is our phase plot. So I'll just go ahead and explain the gain plot. If you can see the y-axis, it is the gain in dB, and the x-axis is the frequency in hertz. So if you can see, the vertical axis, which is the y-axis, represents the gain of the system in decibels. So the gain measures how much the system amplifies or attenuates the input signal at different frequencies. Coming to the x-axis, it's a logarithmic scale representing the frequency in hertz, spanning from around 66.86 microhertz to 8.82 gigahertz. So the frequency scale covers a wide range from very low frequencies, which is sub audio, to very high frequencies, which can be radio frequencies. And then as you can see, the curve we have gotten here as the results. So the red curve shows the gain response of the system across the frequency spectrum. So the gain starts very low, around negative 320 dB at the lowest frequencies, increases to a peak value around 10 kilohertz, as we can see, to 100 kilohertz, and then decreases again at higher frequencies. Coming to the phase plot, the one at the bottom, as you can see, the y-axis, it's the phase in degrees, and the x-axis is the frequency, of course. So y-axis, the vertical axis represents the phase shift introduced by system in degrees. The phase shift measures how much the input signal is delayed or advanced in time as it passes through the system. Coming to the horizontal axis, which is the x-axis, is the same as the gain plot, representing the frequency in hertz on a logarithmic scale. As we can see the phase curve, the red curve shows the phase response of the system across the frequency spectrum. So the phase remains almost constant at 0 degrees across the entire frequency range, indicating that the system introduces no significant phase shift. So what we are trying to say here is we would like to interpret the gain and phase. So let's talk about the gain characteristics. So the system has very narrow band where it significantly amplifies the input signal around 10 kilohertz to 100 kilohertz and significantly attenuates signals outside this range. Coming to the phase characteristics, the phase response indicates that the system does not alter the phase of the input signal much, maintaining a near 0-degree phase shift over all frequency, as we can see. So this bot plot suggests that the system acts as a band pass filter, allowing a specific band of frequencies to pass through with amplification while attenuating frequencies outside this band. The phase response indicates that the filtering does not introduce significant phase distortion to the signal. That's all from me, Doctor. Thank you.